So many of our rational functions are going to have these horizontal asymptotes, and now we need to discuss how we go about locating and describing these horizontal asymptotes. And there's really only 3 situations or cases that we need to be able to work with. So for our upcoming discussion, we're going to assume that our function f is a rational function. So it's one polynomial divided by another polynomial, p of x over q of x. And here we're giving a bit more of a description for these polynomials, p of x and q of x. So we're just thinking about these kind of general forms for a polynomial here. So our polynomial in the numerator is looking like a sub n times x to the power of n plus a sub n minus 1 times x to the power of n minus 1, and so on, until we get down to the end of our polynomial with those smallest terms like a1 times just x to the power of 1 plus a naught, some constant value. And then in our denominator, we have a very similar setup for our general polynomial down here, but now we're using b sub m as our coefficient. So our leading coefficient or leading term is b sub m times x to the power of m. And so these numbers n and m are describing the degrees of our numerator and our denominator separately, and they're not necessarily going to be equal. Kind of the relationship between these degrees is going to help us determine whether or not we have a horizontal asymptote. So then, of course, we have the rest of our polynomial in our denominator. Don't need to describe that. Let's go ahead and describe the first case that will help us in identifying a horizontal asymptote. And so for our first case here, we're assuming that n is less than m. So the degree of our numerator is smaller than the degree of our denominator. This is what we saw in our function 1 over x, right? The constant function 1 is a degree 0 polynomial, so that n value would be 0. And x is, well, x to the power of 1, so that'd be a degree 1 polynomial. And what we saw for our function 1 over x is that its long run or n-term behavior was that we had a horizontal asymptote at y equals 0. Well, that's actually always going to be the case when the degree of the numerator is smaller or less than the degree of the denominator. We'll always have a horizontal asymptote at y equals 0 for those types of rational functions. And so here I just have 3 quick examples of some rational functions: 1 over x, which we've seen before, x over x squared minus 1, and x to the 5th minus 100x squared all over x to the 7th plus 1000 times x to the 5th. What all 3 of these rational functions have in common is that their long-run behavior or the end behavior is described by a horizontal asymptote at y equals 0. So we've already seen that for our function 1 over x, that toolkit function, our end-run behavior is as x heads off to the right or to the left, or as x approaches positive or negative infinity, our outputs, our y values, or f of x is going to approach 0. And well, that's true for our other examples here as well, and it's really true for the same reason in each one. And so it's always happening with these rational functions where we have this difference in degrees between the numerator and the denominator, where the denominator is always bigger, is the denominator grows significantly faster than the numerator ever could as x gets significantly large enough. So we always end up in the situation where we have these relatively very small numbers in the numerator divided by these significantly larger numbers in the denominator, and those types of quotients are always getting smaller and smaller and approaching 0. You can really convince yourself of this further by actually plugging in some values of x. Right, let's look at this last example down here. If x was equal to 1, then that's not a very large value of x, so we wouldn't see any kind of this asymptotic behavior. It wouldn't maybe be very close to 0. But once x gets large enough, we will see this behavior. If you were to plug in x equals like 100 or 1000, we'd really start to see the difference between these quantities involved. If we even took it further than that, plugged in like x equals 1 million or 1 billion, well, 1 billion to the power of 5 compared to 100 times a billion squared is not that different from 1 billion to the power of 5. It's almost not even worth subtracting off that 100 times 1 billion squared. Similarly, in the denominator, it's almost like once x gets large enough, it's not even worth bothering looking at those smaller terms. They do not contribute much significantly to the overall quantity. So it all comes down to the kind of leading term in each. But then you're starting to compare like 1 billion to the power of 5 to 1 billion to the power of 7. You're going to have a lot more zeros in the denominator, a way bigger number down there, and it's going to cause the overall quantity to get very, very small and eventually very, very close to 0. All right, so in our first case, as long as the degree of the numerator is smaller than the degree of the denominator, we'll always have a horizontal asymptote at y equals 0. So as x approaches plus or minus infinity, f of x, or our function, will always be approaching 0. So what if n and m are equal, meaning that the size or the degree of the polynomial in the numerator compared to the polynomial in the denominator are exactly the same? Well, if that is the case, then our function, our rational function, is again going to have a horizontal asymptote. The idea is our horizontal asymptote is going to be given by the ratio of the leading coefficients of our rational function. All right, so here I have two quick examples of some rational functions that satisfy our criteria for the second case here. So in our first example, our rational function is 2x minus 1 over x. Notice how both the numerator and the denominator are degree 1 polynomials. In our second example here, our rational function is 4x cubed minus 10x squared plus 5 in the numerator. And in the denominator, we have 100x minus 10x cubed. So just like in our first example, our second example also has the degree of the numerator equal to the degree of the denominator. They're both degree 3 polynomials. So we will have a horizontal asymptote, but it will not be at y equals 0. It'll be at the y value given by the ratio of the leading coefficients. And so we have to make sure that we correctly identify those leading coefficients to find our horizontal asymptotes here. So in the first one, I think it's pretty straightforward. Our leading coefficient in the numerator is 2, and it's not written there, but our leading coefficient in the denominator is 1. So our horizontal asymptote is at 2 over 1, or just 2. For our second rational function, we have to be careful about the order of the terms here. Remember, we have to identify the leading term by that largest power of x. So in the numerator, that largest power of x is 3, same with the denominator. And those coefficient in the numerator, that number that x cubed is being multiplied by, is 4. So that's going to be the numerator of our horizontal asymptote. And the leading coefficient of the denominator is going to be negative 10. We have to include that sign there, so don't forget that. So the denominator of our horizontal asymptote is going to be negative 10, and we can simplify that fraction to negative 2/5. So for our second rational function here, as we head off to the far right or to the far left, as x approaches positive infinity or as x approaches negative infinity, our y values are going to get closer and closer to this horizontal line described by y equals negative 2/5. So there's a couple different ways we can make sense of or rationalize this second case here. Sorry for the pun, I couldn't help myself. But remember, when we're considering horizontal asymptotes or the end run or long-term behavior of our rational functions, we're only really concerned with what happens when x gets really big, positive, or negative. And as we were discussing in our first case, for these extremely large values of x, all the other terms involved don't really matter. Right? And so there's not a whole lot of other terms floating around. In this example, I still have left up on the board 2x minus 1 over x, but once x gets in the millions, billions, trillions, and so on, subtracting 1 from the numerator isn't going to make a difference at all. So this will basically just simplify to the ratio of the leading terms, in this case 2x over x, which now we can cancel those common factors of x out and be left with our constant of 2. I think that's the most basic way to explain why we're getting these non-zero horizontal asymptotes. All the other terms besides the leading term in the numerator and the denominator are insignificant. We can then get rid of all those other terms, simplify what's left over, and because the degree of the numerator and the denominator are always equal, the powers of x will therefore cancel out, and we'll be left with this ratio of leading coefficients describing our horizontal asymptote. There's a slightly more in-depth explanation, which I'll go into real quick here, that relates back to case 1, and that's that we could actually simplify our rational function here by performing just a little bit of polynomial long division. So let's go ahead and do that real quick. If we actually take the time to divide 2x minus 1 by x, well, how many times does x go into 2x? Goes into it 2 times. Now if we perform that multiplication or division algorithm process, we have to multiply our divisor by that quotient. That gives us 2x, subtract that away from our dividend, and we're just left with negative 1. So what that means is that we can rewrite 2x minus 1 over x as the quotient, that is the answer here, 2, plus the remainder over the divisor. So we can rewrite or simplify these case 2 type rational functions by breaking them apart and writing them in a more proper way. For this example, 2x minus 1 over x, it simplifies to 2 minus 1 over x. And well, now if we're considering the kind of long run or end term behavior of our rational function, instead of looking at it in this form, we can look at it in this simplified or rewritten form instead. Well, what happens to 1 over x as x gets very, very large? Well, we already discussed that in case 1. The numerator is smaller than the denominator degree-wise, so that is going to go to 0. And what happens to the constant number of 2 as we plug in larger and larger values of x? Absolutely nothing. It's a constant, right? Plugging in different values of x doesn't change this thing, so it's always just equal to 2. And that's always how we can kind of think of the second case here. Although once we recognize the second case, you definitely don't want to go through all this division process. Just take those leading coefficients, take their quotient, and you got your horizontal asymptote. All right, so we have one case left to consider here. We've already considered what happens when the degree of the numerator is smaller than the degree of the denominator. What happens when the degree of the numerator is equal to the degree of the denominator. And so the final case is what happens if the degree of the numerator is bigger than the degree of the denominator. Well, when we are in this case, then our rational function is not going to have a horizontal asymptote, but we're still definitely going to be interested in these types of rational functions' end behavior. Their end behavior may or may not be what we call a oblique or slant asymptote, but either way, we'll always be able to determine the end behavior of this third case using some polynomial long division, just like how we discussed for that alternative explanation for the second case. So let's go ahead and consider an example of this third situation or case. So here we have a rational function, x squared plus 1 over the quantity x plus 1. And so here the degree of the numerator is 2. The degree of the denominator is 1. So the denominator is smaller than the numerator. We are in our third case. We are not going to have a horizontal asymptote that our rational function approaches, but we are going to have what we call an oblique or slant asymptote. So now how do we find this so-called oblique or slant asymptote, or this end behavior of our rational function for this third case? Well, we have to first rewrite our rational function in a more simplified or broken down form by performing some polynomial long division. So we have to actually divide x plus 1 into x squared plus 1. Well, that'll initially go in x times. So it'll give us x squared plus x. When we multiply our divisor by that first term in our quotient, and then if we subtract that away from our dividend, the x squareds cancel out, and we're left with 1 minus x, or negative x plus 1 is probably the more proper way to write that. And so now we have to repeat our division process one more time. How many times does x go into negative x? Negative 1 times. Now if we multiply that out, negative 1 times x plus 1 gives us negative x minus 1. We got to subtract that away from our second little dividend here. Negative x minus negative x cancels those out. Then we have 1 minus negative 1, which simplifies to 2. So what that means is that we can rewrite our rational function x squared plus 1 over x plus 1 as the quotient x minus 1 plus the remainder over the divisor. And so remember, the reason why we're rewriting our function in this way is to help us describe the end behavior of this rational function, which is always kind of figuring out what happens as x approaches positive infinity or as x approaches negative infinity. Well, now, what happens to this last piece as x gets really, really large and positive or really, really large and negative is, well, we're in our first case up here, right? The numerator is smaller than the denominator. That little rational function, that fraction off at the end there, is going to go to 0, and what we're left with is x minus 1. And so we know that x is going to do some stuff, x minus 1 is going to do some stuff as x gets really, really large. But what this is really telling us is as these x values for our function get big enough, this last little piece of our function doesn't contribute anything. It contributes things that are really, really close to 0, so we can basically ignore them. So then what does our function look like once we started to ignore this piece? Well, our function looks like that first piece, y equals x minus 1. And so that means if we're to take the time to graph this function, which is going to be the next topic we're going to talk about, then if we graph this line, y equals x minus 1, this line is now going to be the asymptote for our rational function, meaning as x gets really, really large and positive, the outputs are going to have to approach our slanted line here. And as x gets really, really large and negative, we'll have to approach this slanted line and almost become the slanted line down here. Now, whether we approach our slant or oblique asymptote from above or from below is yet to be determined. We got to do a little bit more analysis to figure that part out. The quotient that we get from our polynomial long division is going to be that function that describes the end behavior of our original rational function. So our original rational function here was x squared plus 1 over x plus 1. Its end behavior is going to be exactly the same as the end behavior of this quotient that we found, x minus 1. And so these quotients may change whenever the degree of the numerator is just 1 more than the degree of the denominator. We'll always get a linear function as the output of our quotient, and that'll always give us this linear or slant or oblique asymptote. But other things may occur, like if we have a difference of 2 or more between the degrees of the numerator and the denominator, then our quotient may give us like a quadratic function or a cubic function or some other polynomial. And that polynomial is going to be the descriptor of the end behavior of that rational function.